Alright guys, so we're back. Now, one of you guys asked me to cover a few things from quantum computing, actually, the other course. So I thought I'd look at the notes and see if I can make something of it. And so I went ahead and made some more stuff. But one of the things that you asked me about was, I think I did mention it, but it's worth mentioning again, is that you can't use entanglement to communicate faster than the speed of light. And the way we actually go about seeing this is that something we saw last time, I think it was last time, was this right here, which is that if we have an entangled state, which is described by the density matrix rho of Alice and Bob, then if we want to specifically describe the subsystem corresponding to one of the holders of the two qubits, say Bob, then all we do is trace over Alice's system, which basically means, you know, sum every measurement that Alice can perform. And what you'll be left with is just Bob's system. Now, if we just look at a quick example, not that I'll calculate it explicitly, but like it's a proposal in case one of you guys want to check, is if we have something like this state, for example, which is one of the Bell states, if you had this system describing that they sort of differ in qubits, where if one measures 0 and the other measures 1, or vice versa. You know, if we imagine that they each are separated by a large distance. Well, if you only want to describe one of these two subsystems, so one of the two qubits, despite them being entangled, the way we would go about doing that is that we would simply trace over the other person. In other words, like, you know, if we imagine we can flip two coins, and one of us describes, well, I can flip a heads or a tails, then obviously what does that leave us with? It leaves us with the other person also being able to flip heads or tails. Now, obviously, there's more to it, which is correlations, but if we ignore that for a second, what you'll see is that if you calculate it, it actually comes out to being the identity divided by 2. Um, now, this doesn't seem like that much, but it actually holds a little more meaning than we think. Because this is a density matrix, being described by the identity, that means that in our two-dimensional system, we can actually perceive this. Let me just write up Bob's density matrix. It means we only have diagonal entries, so corresponding to 1/2, with the zeros here. Now, us having zeros in the off diagonal means that if we sort of reduce it down to one system out of an entangled system, we perceive it in terms of its statistics as being decoherenced. So sort of we can't see quantum effects. In other words, if Bob just measures his qubit, which is entangled with Alice's, he can't really gather any information from Alice because to him it just looks like a coin flip. Which is why I'm writing that what Bob sees is a statistical mixture, despite them being entangled. Now, the difference of them being entangled is that if one of them measures, then you can predict the with like 100% certainty the outcome of the other person. But for the individual person itself, it makes no difference, as we can see right here. Now, that was sort of just to recap what it was that I said last time. The new thing we're going to cover today, something extremely fundamental. Like this might be one of the most fundamental things we're going to cover, period, is the Bell inequalities, and specifically from it, something called the CHSH inequality, which is like an abbreviation of four people's names. Like you can look it up. But basically, we should think of this in terms of a classical scenario and a quantum scenario. So let's imagine for a second that we have a Bell state that looks like this right here for Alice and Bob. This Bell state predicts that if one measures 0, the other measures 0, and if not, if one measures 1, the other also measures 1. Now, If we sort of took this state and did a thought experiment, which is what if both Alice and Bob measure X? Well, they should be one-to-one correlated. So we can see that if Alice measures 0, Bob should also measure 0. Likewise, if Alice measures 1, Bob should also measure 1. Same goes for if they measure Z instead. If Alice measures you know, okay, not 0, but like if the state collapses to this measurement, she gets 1, and if it's from this, it's -1. Like you know the value stemming from Z's. But basically what we're seeing is that for this state, both X and Z are perfectly correlated. Now, um, Einstein, Podolsky, and Rosen, their sort of justification for how it could be that these quantum states have these like correlation values was a proposal of something called local hidden variables, or a sort of abstract name for it is local realism. It is sort of a philosophical approach to like a belief of how the universe operates. And now their sort of belief or claim was that yes, these quantum systems have these correlations, but that's just because when they were entangled, they sort of came pre-built with some like unknown quantum value that they sort of always kept to each other until it is that they measured, almost as a sort of instruction that's sort of hidden from the observer until it is that we measure. So we can imagine that we had some like system like this, which got entangled, and then the two systems got spatially separated. Einstein, Podolsky, and Rosen believed that initially what happened here was that they came with like instructions, these two qubits that are entangled, for, if you measure X, then this should come out. If you measure Z, then this should come out. And that was sort of like their justification for the correlations that you see when measuring entangled states. Now, here's the thing. Uh, this is wrong, simply. This was proven wrong, or like in principle, it was demonstrated to be a wrong prediction by Bell uh, via Bell's theorem. Now, but this was just, of course, a theoretical prediction. It's a pretty old prediction, actually. I think it's like 50 years old, if I remember correctly. However, it got proven experimentally, statistically, in 2022, which actually awarded the group who did the experiment the Nobel Prize. Now, this might actually be, at least if you ask me, this is the most fundamental, like demonstrative proof of quantum mechanics, period. Which is why, like for me, like 2022 might be one of the most important years in quantum physics history, period, just because of how like fundamental this proof was. Like by proof, I don't mean like mathematical proof, but like they proved that indeed this local realism isn't real. In other words, the universe is not locally real. Now, what does that even mean? It basically just means that our understanding of like entanglements, superpositions, quantum mechanics, it holds, and we cannot or attribute correlations to local hidden variables. In other words, this theory has effectively been disproven. Now, there are actually several ways of sort of demonstrating this. Bell's theorem is sort of like a major, like higher level theory, but from that you can sort of derive many different versions of Bell inequalities. And the one used in this Nobel Prize, which is also sort of like the one that's usually sort of easy to demonstrate, is this one that we're going to see right here. So imagine for a second that we have our two qubits for Alice and Bob. And let's just say that on each qubit, so Alice with her qubit and Bob with his qubit, they can, upon their qubit, measure either a one sort of operator or the other, or they can like measure a value. And the same with Bob. Now these values can be either +1 or -1. So we're not actually being like concrete. This is sort of just like abstracted as a thought experiment for us to like see the main idea. So um, they each have one of two sort of measurements that they can perform on their own qubit. And now, using this sort of like idea, let's consider a scenario in which we approach this scenario from a hidden or local hidden variable theory. Basically, if we assume that local hidden variables like is a theory that describes the universe, what sort of prediction would it make? And the way that we approach this problem is that we make a parameterization. Basically, if A1 and A2 and B1 and B2, all of these can take randomly a value which is either +1 or -1. If we then parameterize some value like this, what will the outcome be like? Well, if we imagine that we have two scenarios. So scenario one is that B1 and B2 are the same, meaning they are either uh, +1 +1 or -1 -1. Well, if they are positive, then B1 plus B2, or sorry, if like they're the same at least, then B1 plus B2, that should be either the number 2 or the number -2. And this parentheses over here, if they are the same, then the fact that they are discriminated by a negative sign on one of them means that this would result in a value of 2 or -2, and this would be 0. Now, if we imagine the other version right here, you would sort of just have the opposite scenario, which is that this right here would be ±2, and this right here would be 0. Um, and of course, like A1 and A2 can also be +1 or ±2. So this is either plus or minus, and this is either plus or minus. When you sum all that together for like every scenario, you see that the possible outcomes of this parameterization is the value ±2. Now, now that we know this, let's consider sort of, oops, I made a typo. Let's sort of just like look at another sort of parameterization which takes account for like averaging. So like if we have like every possible version of these values, what is the result that we can expect from it? And let's just call that K, which is that we look at this average for A1, B1, A1, B2, A2, B1, and A2, B2. Now, if we take the average of something that can be either +2 or -2, then we would sort of expect that an average would be in a source, if you like did many like measurements, statistically, we would imagine that its absolute value would maximally in the most uncertain, like most unlikely case be 2, which is like if every measurement would correspond to them getting an output value of 2, but like in an average sense, it would, okay, this is really weird to explain, but like if you get, like if you're measuring something and you have like two discrete potential outcomes and you did a lot of measurements, so like one, two, like you got like some tally of measurements for like one extreme value, some tally of measurements for some extreme value, you would expect the average to fall somewhere in between here. And in the most extremely unlikely scenario, all of your outputs would be in either one or the other. In other words, you wouldn't expect to get values outside the possible range of outcomes. I hope what I said makes sense, especially with this like really weird, like quick um, illustration I tried to do. But in other words, the prediction from local hidden variables is that the parameterization of this value, oops, I don't know why I wrote S, hold on. you would expect the absolute value of this parameterization to be at the very least, like maximally 2, but like somewhere in between. Now, given this approach or belief in how the universe works, this is the result we predict we would get from statistical measurements. Now, let us try to compare that with a quantum mechanical prediction. What does quantum mechanics say about what we can expect of like correlations in measurements? And to do that, because statistics should, or like the laws of physics should be applicable to all states, we can't just start out by assuming some random state, so long as it's just two qubits that are correlated. So let's just take this state right here. This is sort of a state that's very convenient to calculate, which is 0, 0 or 1, 1 with some relative phase on it, which is e to the I pi divided by 4. Now, if we make some concrete potential examples of what these operators could be in a quantum mechanical sense, we could, for example, assign Alice's potential ones to be that she measures her qubit either in sigma x or sigma y, and Bob's could be in sigma x and sigma y as well. How would this sort of, you guys have seen these gates before, right? Just in case you haven't, I did write it out. That sigma x, which is the Pauli x gate. Actually, I think you guys write just like capital X or capital Z, or sorry, capital Y. But Pauli's X gate is basically just what corresponds to the quantum NOT gate, and the Y gate is the same except there's a phase on it, depending on the state of the qubit in the computational basis. Now, if we start out with a scenario that looks like this, a quantum mechanical prediction instead would have your averages come out to be um, what's this called? 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, and negative 1 over square root of 2. Now, if you take the sum of these in accordance with this parameterization that we made up here, basically if you plug in these values for these terms, you would actually get an outcome which is 2 times square root of 2. Now, 2 times square root of 2 is not smaller than or equal to the number 2, which is the value that we got as a prediction from a local hidden variables theory. In other words, we say that this inequality that was predicted by the local hidden variable theory, it has been violated, um, which basically just says that quantum mechanics is statistically incompatible with a theory which asserts local hidden variables to quantum systems. But okay, that just means we can conclude that quantum mechanics violates local realism. However, this is just a thought experiment. So like, does it actually tell us anything about how the world works? Well, not really. And that's because the way we actually figure out how the world works is that we go into a lab and we perform an experiment. And that is exactly what was done, actually, which is why I come back to this point right here. That was what that was the sort of experiment which resulted in the group who did the experiment getting the Nobel Prize back in 2022 because they performed this exact experiment, I think it was using light, and they indeed performed very careful, very fine measurements and found that indeed the statistical measurements you see are sort of incongruent with the expectations that you would get from local hidden variables. In other words, uh, I can't remember if they did a slightly different setup, but in essence, what they sort of got was that they measured a result which came out like this. In other words, they demonstrated the inequality in their experiment. If you sort of look up the experiments on the Nobel Prize's website, there are actually two different documents you can download. There's a highly technical document for people who are sort of in the field and who know the esoteric knowledge behind it, but there is also a layman's version which sort of explains the idea to people who don't know anything about physics, which is not to say that you should read that one, because I suspect that we probably do know enough technical stuff to understand the technical paper, but it's just a recommendation if you're curious. But I hope this sort of helps demonstrate why it is that, you know, I wouldn't exactly say that quantum mechanics is true. We sort of have this like discussion in science, which is that you can't prove anything, but you can only disprove stuff. Now, like, I actually myself, I don't know if I agree with that or not, but at the very least, what this result goes to show is that local hidden variables has been disproven. Now, this is, one of Einstein's very few blunders, but despite it proving Einstein of all people wrong, like I am personally very impressed with the results, and I hope you are as well. Anyways, I hope this helped, and take care.